Okay, hello everyone. Let's start today's discussion. Uh, Today, we are going to continue our discussion about the root locus method. So far, we learned what is the root locus, the definition, and we saw how it could give us a good understanding of the dynamic of the poles and zeros when we don't have an static system. So we have like a variable parameter in our system, and we show it by that k, if you remember from the previous session. Now, today we are gonna learn a little bit of more easier way to sketch the root locus graph. In previous session, we just tried different numbers for k and basically find the poles and zeros, which most importantly is zeros, the poles of our system, and find out what is the trajectory of those poles when the k changes. Now, today we are going to learn an easier way using the properties of the root locus graph. Now, we know that when we wanted to draw the root locus, we are going to consider the feedback, okay, the closed feedback for our system. So what we wanted to consider was when we have this is the simplest way. Like we have draw it in a better place. We have a forward pass. We call it g of s. We apply the parameter k as a gain. And then we use a feedback pass, the transfer function of like h. And that way, we basically created a feedback, a closed feedback system, a closed feedback loop for our open loop transfer function, which the transfer function of such a system, such a closed loop system was the forward pass divided by 1 plus, the plus is because we have a negative sign here, forward pass times the feedback pass. Okay, that was what we talked about so far about what we are going to do. This is the definition, basically the definition of root locus method. Now, we said we wanted to, what's important for us is the stability. Okay, so what we want to do is to find out what is the behavior of the poles in our system. And we know that the poles are basically the zeros of the denominator of our general transfer function. So what that means is that the whole analysis is over the condition of having 1 plus k forward pass, feedback pass, the denominator of general transfer function, to be equal to 0. Correct? That way was when we find out what are the poles are. Now, look at this equation. When you see this equation and try to find the condition that actually make this whole denominator equal to 0, you can see that we can play around a little bit with this. So basically the key k, g of s, h of s on the poles are going to be equal to the -1. It's a simple kind of mathematic trick. We just transfer this 1 to the other side of equation. Now, what that means? That means we know that the K is a parameter, and in our simplified situation is simply a gain, which means it's a constant function. It is a constant value, a parameter, correct? Now, that means the poles are the S's that makes this G times H equal to 0. Okay? So those are the poles. Now, when you look at this value, when you look at this K, G, H, on those specific S's, which are basically our poles, this is going to be a complex number. Are we good? We put in any arbitrary or any chosen S, okay, inside the GS, the result is going to be the output of this function as S is equal to, for example, let's go actually over that. The G of S, when S is and like A plus JB, when you put in the S inside the G, is going to be another complex function, another complex number, which is like, for example, C plus JD. Okay? Same goes for the H. What that means, and these two are multiplying by each other. So the whole thing is going to be, again, a complex number. And the K is just a constant gain. So everything here, the result on each specific S would be a complex number. We learned that we can represent any complex number with its phasor equivalent, that vector that we defined. Remember that? So any K, G, H on any specific S is going to end up as a vector with a magnitude and a phase. Are we good? Now, look at this equation. That M theta is equal to 1. What that means is equal to -1, actually. What that means? That means the amplitude should be 1. Are we good? The amplitude should be 1. Now, let me actually elaborate that. We have our Cartesian system. -1 is that vector. Are we good? This is the vector from 0. This is -1. The amplitude is simply, you can see the amplitude of this vector should be equal to 1. That means the amplitude of that K, G of S, H of S on any point should be equal to 1. These S's that satisfy this condition are the poles, okay? So remember that. It's not just any arbitrary S, okay? We said this is the condition that we already met, which is the definition of the poles, the condition that we find the poles. So if there is such a condition, that means the S's inside this function are the poles. So if we have the poles, we wanted to evaluate the poles themselves. That means, following this condition, the amplitude of K, G, H on those S's, which are the poles, should be equal to 1. Now, this is our vector. This is the theta of that vector. What is the theta? It's very easy. It 180, correct? So the theta of those poles should be 180. Is it just 180? Or it could have another theta and still satisfy the -1 vector. Negative 180. Negative 180 is also correct. What is the negative 180? We're just rotating, right? Okay. So it could be 180, or we can turn a whole cycle and come back to this point. Now, what is the theta here? 360. 360 is from here to here. No, we circle back 360, and our original angle was already 180. So it is gonna be 540, right? So we go from 180 and add 360 to it, right? So it could be also 420. Now, what is 420? If you wanted to represent it by original value of theta, what number times this 420 would what number times 180 would result in 420? Is 3, right? Now let's turn another row. That's
540. 180 times 3 is 540.
Yes.
Put 40.
Oh, sorry. Now, what if we go another turn? So we rotate 2 cycles. Then it become what? We are gonna add 360 to that 540, right? We turn another 360. So it's gonna be 900. And that 900 degree is basically 5 times 180. Now, look at the trajectory. The theta of this vector only can be the odd number times 180, right? So the general condition for the theta of S's that satisfy this condition, meaning the poles, the general theta of all the poles, the general formula for that is any, let's see, with another, any odd number times 180, correct? Now that alpha would go from 0, which if you put 0, it's 180 itself, all the way to infinity. Are we good? So now we can see that if we want to find the poles in our system, that means the theta on those S's should be an odd multiplication of 180. Alpha is a number from 0 to infinity. We just wanted to create a odd number, because we see if we rotate, we only would land on an odd multiplication of 1/8. So this is just the general formula representation of odd number. Okay, and the alpha goes from 0 all the way to infinity. Any number you put at alpha, you would end up with a odd number as a coefficient of that one. Okay, what that means? Let's look at it other way around. That means if we have any S in mind and we want to see if that S is gonna be for any type of K, is gonna be on that trajectory of the pole, that means that S could be a pole of system. It only happens if that S, if the theta of that S in this formula, so the theta of this formula for that S is an odd multiplication of 1/8. So this is the condition that we can see if any S's has a potential of being pole or not. Are we good? Now, if that S satisfies this condition, okay, that means it is going to be a pole. Now, who can tell me how we can find the K that makes that S a pole? Remember, when we had this, the example that we had, let's say we had two poles, we changed the case, the previous example that we made, and saw that each poles would have such a trajectory. Do you remember that? Now, let's say we have an S, let's say here. Okay? But we don't know the trajectory. We want to see if that S has a potential of being pole or not. We calculate the theta, which is the phase of this KGH for that S. Okay? And if that theta is an odd multiplication of 180, that means that S has a potential of being a pole. Are we good? Now, one thing that's missing is when that S would be a pole, which depends on the value of the K. Correct? So anyone can tell me, using this formula, this condition that we have, how we can find the K that would make that S a pole. So what is the K, for example, here? For what K our pole move to this specific S? Look at the condition that we have and tell me how you can find the K for that specific S. So this is actually a specific S, let's call it S1. And this is actually the S1, for example. What will be the value of K that makes this S1 a pole, or like move the pole to that specific S? How you can find it? You don't know the trajectory. This is, I just use this example that we solved before for your intuition. You don't have this plot.
You can solve for K.
You can solve for K using this condition. You have your S, That means you can find this one, the amplitude of that one. K is a constant number. You can bring it out, right? That means that K or that specific number is 1 over the amplitude of G and H, the function that we have here, equal to 1, which means K is equal to 1 over that amplitude. So for each S, you would find the theta of the output of our transfer function, our KGH, if the theta of the output is an odd multiplication of 180, that means that S has a potential of being a pole. Now, for what K it become a pole, you can use the condition of amplitude to calculate the K that would make that S a pole of the system. Are we good? So this is how you can analyze without having the sketch, the Root-Lucas sketch, how you can analyze any arbitrary point to see if first has a potential of pole, and if it's a pole, for what K it's become a pole. Are we good? Any question about that? No? Now let's use an example. Let's go over an example. Can I raise the board? Let's use an example to actually find out what we mean. Let's say our transfer function, an example that we have as a transfer function, is K times, this is the closed loop already, we did the closed loop, so it's the K over 1 plus KG, okay? KG over, okay. So it's gonna be K times S plus 3 times S plus 4 over 1 plus K S squared plus 3 plus K S plus 2 plus 12 K. Yeah, 2 plus 12 K. Okay, now I don't want to do the algebraic kind of like solution and find or like, you know, divide this whole situation to find out what are the poles are. You can find it. But if you find that pole, those poles, you can see if we want to analyze the point S1 equal to -2 plus J3, this is our S. We wanted to determine that it has a potential of, does it have a potential of being a pole or not? Now you put that S inside your inside your transfer function. Okay. what would be the theta of the result? We already covered that. If you want to find the theta of the result, that means you have to find the theta of the denominator. Do you remember that? It was the summation of the theta of the denominator minus summation of the theta of the denominator. Do you remember that? Okay, so we can run the analysis. If you do the calculation, we are gonna, this is the second order. This is also a second order. That means we have two theta in the denominator. Let's say theta 1 plus theta 2. And we have two theta in the denominator. Theta 3 minus theta 4. Now, you can put the numbers in. Okay? Remember, we are gonna use k equal to 0. Do you remember that? What we did before? Oh, sorry. Any value you can put that. K is a constant number. Okay, so you can put it 1 or any value. Okay, because if you put a 0, that means it would kind of like clear up the whole denominator. So you don't put that the 0, any value for k. Okay, if you do the calculation, theta 1 would become 56.31 degree. Theta 2 would be 71.57 degree. Theta 3 is going to be minus 90 degree, which is that minus is here. So this is going to be 90 degree. And theta 4 is going to be 108.43 degree. Now, this is a simple summation and subtraction. If you do the subtraction, the result is going to be minus 70.55 degree. Now, is this S has a potential of being a pole? No, because the theta on this S is not an odd multiplication of 180. Okay, so that S is not going to be a pole. Now, is there any question?
Wait, how you get those angles?
You put the S in the denominator. This is going to be a complex number. So this is going to be another complex number. Like, for example, if you put minus 2 plus J3, this become is plus 3. So this become 1 plus J3. Okay, and this one become 2 plus J3. Are we good? And we said we can consider any K. Let's say it's 1. Let's say K is 1, okay? Now, what would happen here? You have a theta here. You could calculate the theta of this 1 plus J3, and it's going to be, the theta is going to be tangent inverse of 3 over 1. So tangent inverse of 3 is going to be 56.31 degree. Same goes for this one. Tangent inverse of 3 over 2. And you are going to have your theta. Same goes for the bottom one. If you put k equal to 3, you are going to have 2s squared. So, sorry, k equal to 1 is going to be 2s squared, 4s, and this one is running 14. Are we good? So you can find the zeros for that, and basically, let's say the zeros of that function is a and b. Okay, so this become s plus b, s plus a, right? So you can put in the s and find out what is going to be the theta of each of those terms. Are we good? Now, any other question? No? Go ahead.
Can you run through again how you got those cases like one plus J3 to
I just
Yeah.
put the S1 as S. This
Oh,
is
okay.
-1 plus J3 plus 3. So it would change, it wouldn't change the imaginary part, it just change the real part. Are you good?
Yeah.
Any other question? No? Okay. Let's move on to the properties of root locus and see how we can use those properties to sketch the root locus without solving the whole situation for different case, like what we did in previous session. Okay. In root locus, about the root locus, we have like several properties, 5 properties or 5 rules, okay, that would be the characteristics or properties of that whatever arbitrary root locus sketch that we have. Okay, so these 5 rules applies to every root locus, different system, different root locus that you have. These are general rules. Okay, now rule number one is that in any root locus, okay, the number of the branches that we have, okay, is going to be equal to the number of pole or zero, whichever is bigger. So let's say we have in a system with n poles and m zeros, okay, the number of branches that you are going to see in your root locus is equal to n if n is bigger than m, and is equal to m if m is bigger than n. So whatever this is the number of the poles, number of the zero, whichever is the bigger one would be the number of branches that you're going to see in your root locus. Are we good? Now, rule number 2. The root the root locus is always symmetric or symmetrical in respect to real axis. Anyone can tell me why it's always symmetrical? So that means, what that means is if you have a sketch, this is the real axis, okay? The root locus sketch should be symmetric in respect to this axis. That means whichever you have in a top part, you are gonna see the mirror of that in the bottom part. Anyone can tell me why we have this rule or this property for root Lucas?
Could the poles doesn't count?
Sorry?
Could the poles equal 0?
The poles are equal to 0, but we have several poles. We can have some poles in real axis, okay? Or some poles as an imaginary axis, in any imaginary number. So we could have a pole as a real number, or we could have a pole as a complex number. So why root Lucas is always symmetric in respect to real axis? What is the properties of these two complex ones? They are conjugate of each other. Okay? Whatever is in the real axis, you can imagine that it would not affect the symmetrical behavior because it is always symmetric. Whatever branches that you have exactly on real axis. Are we clear on that? Now, the branches that involve this imaginary number, because we cannot have a complex number without having the conjugate of that complex number, that means we always have a symmetric part. Are we good? So this is the rule number 2. Rule number 3 is any branches on the real axis only exist on the interval or section, let's say section, that have odd number of zeros and poles on the right side of that section. It's a little bit confusing that it's made the statement. Let me show you as an example. Let's say we have a real imaginary system. For example, we have a 0 here, a pole here, another pole here, and another 0 here. Okay? We look at the real axis. You see, we have one section from this 0 to infinity, right? We have one section here. We have one section between these two between this 0 and this pole. Okay, this is one section all the way to infinity. This is the second section. We have another section between these two poles on the real axis, and another one between this pole and this 0, and another one between this 0 and minus infinity. So these zeros and poles on the real axis, okay, they divide the real axis to several sections. Okay, now we want to see without calculating the k or solving the whole system for all the s's. we want to see if these sections are going to be in our root Lucas or not. Meaning, would we have a pole for any k in this section or not? For example. Now, the rule says that the branch exists on that section if we have the odd number of poles and zeros on the right side of that section. Right? Now, look at this section. Do we have any poles and zeros on the right side? We don't have. So this part, in this specific example, this part is not going to be in our root Lucas branches. So we are not going to have any branches here. Are we good? How about the second section? The second section have 1 0 to the right of it. 1 is odd number. That means there are going to be a branch here. This section has 2 poles and zeros, so there are not going to be a branch in this section. This one would also have a branch because we have 3 poles and zeros on the right. Is that clear what we mean by this rule? Now? Are we good? This is section 1. Let's say this is section 1, section 2, section 3, section 4, and section 5. Okay? The rule is the section on the real axis, okay? We don't talk about the complex number. On the real axis, the section would have a branch on it if there is an odd number of poles or zeros, poles and zeros actually, okay, to the right of it. This one goes from this 0 to infinity. There is no right of it actually, okay? So we are not going to have any poles or in this section. It doesn't matter what is the k. Are we good? Now, this one has 1 pole to the right. That means for some k, we are going to have poles in this section. So this section is going to be in our branches that we are going to have. This section is going to be a part of root Lucas graph. Section 3 has 2 poles and zeros on the right. So this one would not be in our root Lucas graph. Section 4 has 3. So it would be part of our root Lucas graph. We are going to have a branch on it. From this 0 to minus infinity, we have 4 poles and 0 to the right. That means we are not going to have any branches in our root Lucas graph on this section. I'm talking about the real axis. I'm not talking about like graphs that exist, like, for example, it could be here. Okay, in the imaginary part, beside, in a complex part, beside the real axis, exactly the exact real axis. We are only talking about the real axis. Are we good? Any other question? Now, rule number 4 says that the branches, every branch in our root Lucas every branch in our root Locus graph will start at the pole and end at a zero. If you remember the example that we solved before, okay, we start with the k equal to 0 and go to the k equal to infinity. If you do that for any system, you would see the trajectory of the poles, that the sketch that we have for root Locus graph would start at the pole and it would end at a 0. Are we good? Now, you might say, okay, what if we don't have a 0 or we don't have a pole? If we don't have a pole, actually, it doesn't mean anything because there's no instability. Okay, so let me try another way. What if we have no zeros in our system, like the one that we had as an example before? So we only have 2 poles. Using the rule number 3, we know that this graph includes this section. Remember, odd number of poles and zeros at the right. This one doesn't have anything, so it's not included. This one is included. This one has 2 on the right, so it's not included. If we don't have any zeros, okay, that means how we can find, based on the root Locus, that where these graphs, which means the trajectory of these 2 poles, okay, would end. If you are short for zeros or poles, you can say that the poles or zeros that you're short for are in infinity. Okay? Not real axis exactly infinity. It doesn't matter. It's exclusively in a real axis infinity. It could be anywhere that is equal to infinity. Remember the example that we had before. When we change the k, we find out that one of the poles goes up and another one goes down. Do you remember that? The examples that we saw for the second order system that we had in previous session. So, for example, these poles, they started from the pole and gone down to an infinite number and basically minus infinite number. The other one, it started from the pole 2 and went to a positive infinite number. So if, for that rule, if you're short of 0 or pole, you can compensate that by considering the poles and 0 that you need is in infinity. Are we clear? Now, let's say another example. Let's say this one we are short for a pole, for a 0. Let's say we are short for a pole. Meaning, for example, we have 1 pole, but we have 2 zeros. Okay, we know that based on the rule 4, the sketch should start from a pole and end to the zero. Are we good? Now, what would happen if we are short for a pole? First of all, using the rule 3, we know we are not going to have any branch on the real axis from this pole to plus infinity. This section would be in our the sketch. This one is not, and this one is it is. Are we good? We said, look at this section. We said every pole, every graph, every branch starts from the pole end to the zero. So you can imagine that by increasing the k, this is the direction of that branch. It starts from its pole end to the zero. Very good. Now, this one, because the end should be a zero, that means we should have another pole that would end up to the zero. Are we good? Because we are short for a pole, we consider that there is a pole in infinity, okay, that would end up coming back to this zero. Is that clear? Any question about these 4 rules? The rule 4 says every branch that you have, okay, should start at a pole and end up at a zero. In this example, we know, based on the rule 3, that this section is part of our sketch. Correct? But there is no zeros in that section. This section doesn't have any. This section also doesn't have any branch on it because of the rule 3. Okay? So this section would have a branch on it, but we don't have any zeros in that section. So if we start from this pole, where we should end up? If we are short for a zero, we can consider that, okay, we don't know, we can't find it, but there could be zeros in infinity, okay? Infinity is a concept, not a number, okay? There are going to be a zero in infinity that these poles can end up with. So one pole goes here, another pole goes to the left, another pole goes to the right, and in the point that they met, one of them goes to a zero in top infinity, plus infinity, another one goes to the negative infinity. Here we are short for 2 zeros, right? So we can consider a zero in plus infinity and a zero in minus infinity. Okay? And each of those poles would end up on those zeros. Any question on that part? Now, in this example, from rule 3, again, we know we are not going to have any branch here. We are going to have a branch here, not a branch here, and we are going to have a branch here. Here, you see 3 poles and zeros are on the right. So there is a branch here. Now, in this branch, we have a pole and zero. So it's easy. We know this pole would end up in this zero. Right? But this zero, which is the end of a branch, does not have a finite, the pole that we can see, a finite pole. So we could start from that pole and end up in this zero. So what we are going to say is that, okay, we don't have a finite pole, but who knows? We might have a pole in infinity. So we can consider a pole in infinity, and this branch would start with that infinity pole and end up with this zero that we know. Are we good? Is that clear? Did I answer your question? Any other question for those 4 rules? No? Okay. Now let's look at an example graph. I'm gonna erase this one and try to see how we can sketch the root locus without calculating for each k. Let's say we have 2 poles here and 2 zeros here. Okay? Now, using rule number 3, would this section be on our, would include any branch on our sketch? This section? No? Okay, so we don't have any branch here. How about this section? It has a branch. Okay, so we have a branch here. This section has 2 poles. It doesn't have it to the right, so there is no branch here. This section has 3 zeros and poles to the right, so we have a branch here. Are we good? Now, we said that the poles would start from the poles. The sketch would start from the poles. As we increase the k, it would end up to a 0. So we know that the trajectory would start from these poles. And since we only are allowed to move in this section, on this branch, that means one of them goes to the left, another one goes to the right on this branch. We know the sketch should end up, end up to a 0. There is no trajectory here, so this trajectory should only end up to those zeros. Now, when they collide here, where those poles should go? Here, in this branch, we don't have any zero. So these poles are gonna collide to each other. They're gonna meet each other at a point. After that, where they should go? Infinity. So one goes up, another goes down. Correct? Now, what about these zeros? This branch would end up in 2 zeros. That means here, we have 2 branches that start from certain poles that would end up in these 2 zeros. Where those poles came from? Again, infinity. Not real axis infinity. There is no branch here. Okay? So we are gonna have a part of a graph that comes from infinity, for example, to those zeros. But I want to go back, because we use the infinity, but I want to go back about when we could have an infinity and when we should not have an infinity. What was the situation that we had poles that goes to infinity or comes from the infinity? On what condition we have those? Why these poles goes to infinity? Because we are short for 0. Why the other example that I erased had a pole coming from infinity? Because we were short for poles. Remember? Now look at this graph. We have 2 poles, 2 zeros. Are we short for any poles or zeros? 2 poles, 2 zeros. Are we short? Anyone can have any opinion on that? 2 poles, 2 zeros. Are we short for a pole or zeros? In this example? In this example, we had 2 poles, no zeros. In the other one that I sketched, we had 2 zeros and 1 pole. So here we had 1 pole, we were 1 pole short. Here we had 2 zeros short. Are we short in this for polar zeros? In this example, we have 2 poles, 2 zeros. No. What that means? That means the trajectory, okay, do not satisfy the condition of being short. So the branch could go to infinity. So if these 2 branches that leave this section and enter to these 2 branches that enter to this section are not allowed to go to infinity or come from infinity because we are not short for any poles and zeros, where those branches should goes and comes from. This is, we said, every branch starts with a pole, ends with a zero. This is the trajectory of the first one. This is the trajectory of the second. This is the trajectory of the first pole, first zero, and this is the trajectory of the second zero. This pole goes here and goes up, leaving the real axis. Rule 4 says it should be end up in a zero. Where this should go?
Before Z.
To one of the zeros that has a trajectory in. This one also should go to the other zeros that has a trajectory in. Are we good? Any question? So, in a system with n poles and n zeros, the number of the branches that we have is whichever is the bigger one, n or m. Now look at this one. We have 2 zeros, m is 2, and n is 0. So we should have 2 branches. 1, 2, 4. Correct? Correct? Here, we have 2 zeros, 1 pole. N is 2, m is 1. 2 is bigger than 1. So we should have 2 branches. 1, 2. 2 zeros, 2 poles. The bigger number is 2. 1, 2. Are we good? Rule number 2 says it should be symmetric. You can already see that the trajectory always is symmetric in respect to the real axis. Same is here. We actually don't leave the real axis here, so it is intrinsically symmetric. And this one is also symmetric. So these two should be mirroring each other. Forget about my bad drawing, okay? These two branches should mirror each other. Are we good? Rule number 3. Any branches on the real axis only exist on a section that have odd number of zeros and poles on the right of it. Here, there's 0 pole and zeros, so we don't have any section here. Here, we have it. Here, we don't have any branch. Same goes here. Based on rule number 3, we don't have anything on this part of the real axis. We have a branch on this part, no branch on this part, a branch on this part. Here, no branch, one branch here, no branch, a branch here, no branch. Rule number 3, correct? Rule number 4, every branch in our root locus start from the pole and end to the 0 at 1, 0. We start from the pole, we don't have any zeros, we're short for zeros, so we consider there is zeros on infinity. So we start and go to infinity. Start, go to infinity. Are we good? This branch, the rule is to start from the pole and to the infinity, into the 0. We're starting from this pole, and we have a 0 on the branch, so we are going to end up to the branch, to the 0. This one, we are short for a pole. This is not the trajectory, okay? This is the infinity. The trajectory is here, okay? It should end up to 0, but where should it start? We don't have any pole for this 0, so we consider there is a pole in infinity. Here, branch is here. We know we should start from the pole, so these two poles would start the branches. Don't have any branch on this section. We have a branch in this section and don't have a branch in here. This branch should end up to the zeros. So there are a source out there that would end up to these two zeros. And since we are not short for any zeros and poles, 2 and 2, that means we should not consider infinity as a 0 and pole. We already have enough finite 0 and pole. So that means the branches that getting out from this section should get in to this section. Are we good? And we know that it should be symmetric. So it should mirror the top one and bottom.
How you know which one goes up, go down? With the pole.
It's based on the K. You can put a certain K in your circuit and find out the trajectory of the pole. So for K0, this is pole number 1, this is pole number 2. You can consider like pole 100. Okay? And see what would be the value of this pole 1. Is it going to be a negative imaginary part or positive imaginary? Are we good? Any other question? Well, we are out of the time. At next session, okay, because here we see we are leaving the x-axis also over there. But you can see that here we leave with a 90-degree kind of like a phase. So the sketch would leave the real axis in a perpendicular way, but this one, okay, has a little bit of curve after. Okay, how we can find out what would be the curves, okay, on the trajectory? We are gonna talk about it in the next session when we talk about the asymptoid lines of the curve. Any question? No? Okay, so this is for today. If you don't have any question, thank you very much and have a great rest of the day.